Suppose that psi is given a given state function. Psi is a solution of the Schrödinger equation, as all state functions are. Now, for some purposes, we write psi in this form. Where the functions on the right side are eigenfunctions of another operator A with eigenvalue Kn. There are infinitely many terms here on the right side. We are assuming the functions are given. Psi is also given. The constants C1, C2, and so on are called coefficients, and they are unknowns. Unknowns are the coefficients, which are C1, C2, and so on. Now, the expression on the right side is called expansion. This is called expansion, and this expression, all of it, is called expansion of psi into a linear combination of eigenfunctions. Depending on the functions f1, f2, etc., and psi function, it is possible that all coefficients could be non-zero, or in some special cases, only a few of them can be non-zero. All these depend on which operator we have selected and its eigenfunctions, which are used in this expression. We are assuming the eigenfunctions Fn to be normalized. In other words, normalized, and we are also assuming psi itself is normalized too. All right, now for this expression to be useful for us, it is possible to, it should be possible to calculate numerical values of the coefficients. So calculation of the coefficients we use two basic facts for this calculation. One is the functions, the given functions f1, f2, f3, and so on, they are all normalized, which means this property is satisfied. Second fact we are going to use is the fact that the set of eigenfunctions f1, f2, f3, and so on must be orthogonal. Orthogonality. Why? This is a basic fact for any quantum operator. The eigenfunctions of any quantum operator form an orthogonal set. What does it mean? It means this. If you take two different functions, which means if n is different than m, in that case these two functions will be different, the value of this integral is 0. This is orthogonality. Okay? Okay. Now, to use these facts, we take this expression and then multiply from the left with one of the functions, f1, f2, f3, etc. Let us say it is, we take nth function to make it general. We multiply with complex conjugate of nth f function, left side and also right side. So we have C1 times now we integrate both sides. Now, we are assuming psi is known. The functions f, all of the eigenfunctions are also known, explicitly given to us. Therefore, everything is known in this factor, and this integration can be done. On the other side, how many integrals do we have? Infinitely many, because this expansion, in general, contains infinitely many terms. However, the integrals are very easy here because of the orthogonality property. There are infinitely many integrals here, but only one of them will be non-zero. Which one? The one in this summation in which this function is, if f2 or f3, etc., if it is the nth function, then that will be non-zero. All the others are going to be 0 because of this orthogonality property. So only one term, and it will contain the coefficient Cn, and it will have this. But we are saying that these functions are normalized. Therefore, this value of this integral is 1, which means we will obtain the nth coefficient. Therefore, to calculate value of C1, this is f1, the first function, times psi. We integrate this definite integral, find a number, that's the numerical value of C1. To get C2, we repeat this procedure. This time we put f2 here and do the integration, obtain value of C2. And so on. This way, evaluating these different integrals, we can calculate numerical values of all of the coefficients. Now, let us turn back to the same question. What happens if this operator A, whose eigenfunctions are used in this expression, if this operator A commutes with Hamiltonian? If A commutes with Hamiltonian, what was the consequence? A and H have the same set of eigenfunctions. In that case, this integral would be very, very simple, because psi would be proportional to, let us say, nth function here. And only one of these coefficients would have been would be different from 0. Why? Because psi itself is going to be one of the eigenfunctions of A, because the A and H commute. And then only how can we express it? Say if psi is proportional to F3, then the coefficient C3 will be different from 0, but all the other coefficients are going to be 0 because of the orthogonality. All right? So in this case, just one coefficient will be different from 0. But for this to occur, the operator A must commute with Hamiltonian. If A doesn't commute with Hamiltonian, then all of the coefficients in general are going to be non-zero value. Now, having obtained how to calculate the coefficients, so let us write it here once again. This is how we calculate the coefficients. Now, we have already said that the state function psi is already normalized. So it itself satisfies the normalization condition. Let us express that condition using the expanded form, using the right side here. Then we will have C1 times F1 plus C2 times F2, and so on, complex conjugate times itself. And this must be equal to 1. Now we expand this, expand the integrand here, remove the parentheses, in other words, and then do the integration using the fact that the functions obey orthogonality property, and also they are normalized. Maybe we can directly use this expression for this purpose. Let us just keep the psi symbol over there. When we take the complex conjugate of this term, we will have this. C1 star times F1 star plus C2 star times F2 star. Complex conjugate of a sum is the same as complex conjugate of the added terms, and the complex conjugate of a product is the complex conjugate of each factor multiplied. These are simple properties from complex numbers. Now, this way it is easy. We have, because the coefficients are constants, we can take them out of the integral sign. C1 star times F1 star times psi plus C2 star times F2 star psi d tau. There are how many such integrals? In general, infinitely many such integrals. But these integrals are not complicated. You see, the value of this integral here, look at the coefficient expression. So what can we write here? Which coefficient is this? C1, right? The value of this integral is again similar to this expression, which is the value of coefficient. So this is C2. Same expression is true for all the infinitely many integrals. So as a result, what do we have? For a complex number z, this expression, complex conjugate time itself, is called the magnitude square, and it is written as, this is a positive definite real number. We have such terms here. C1 star times C1, we write magnitude of C1 square plus C2 square, and it continues like this. The sum of the squares of the coefficients is equal to 1. So we have this relation. Normalization of the state function psi implies that the sum of these squares of the coefficients must be equal to 1. Whenever some summation, whenever some terms are added and the result is 1, we think about probability, because the total probability for an event is always 1. So these squares sum of the squares of the coefficients gives 1. So let us remember what was it. The psi was expanded this way. The square of any one of the coefficients is interpreted as the probability of finding the system in that eigenfunction. For example, C2 square, absolute value squared, is interpreted as the probability of finding the particle in the eigenfunction of A, which is F2. And you see the sum of the probabilities, which means sum of the squares of the coefficients, is equal to 1. Now, related with this, let us look at the average value expression, which is this expression. But when we use the linear combination, we have the operator A times psi. Let us keep it this way. Now, we can simplify this in the following way. A psi equals A C1 times F1 plus C2 times F2. Now we operate inside. Operators don't do anything to constants, remember. So all the coefficients can be factored. So C1 times A F1 plus C2 times A F2. This continues like that. Now, using the fact that these functions satisfy the eigenvalue, eigenfunction relation for the operator A. So, can we simplify this term? Instead of the operator A, F1, can we replace it with a scalar? K1 times, yes, K1 times F1 because of this relation. Similarly, can we replace this with a simpler expression? This is K2 times F2, and so on, K3 times F3. So now, we can write, what we do is, we take this expression, simplified expression, and replace and put it here to A psi. So what will happen is, here put K1, K2, and of course this is no longer 1. Remember, this is average value. Take the complex conjugate. So it is this integral. Now we expand. All right? In other words, we multiply. Multiplication, for example, this term, when you multiply with all of these terms, what kind of expression are you going to obtain? F1 star times F1, okay, and then F1 star times F2. But then this is integration. If F1 star times F2, value of the integral will be 0 because of orthogonality. There are infinitely many terms here, F3, F4, F5, but you are multiplying all of them with F1 star. So all those integrals are going to be 0. So if you imagine this, multiplying and then obtaining the integrals will be of two types. One type of integral will be two different functions are multiplied in the integrand, and the value of the integral is going to be 0 because of orthogonality. The second type of integrals will contain the same function. For example, F1 star times this F1. That integral So here, C1 star times C1, by definition, C1 squared. There is a K1 here, and this integral, when we expand this, it is the first term. But the value of this integral, what is it? It is normalization integral, isn't it? And we are told that all these eigenfunctions are normalized. Therefore, all such integrals will be 1. There is going to be like C1 star times F1 times this term, F2. That integral will be, because F1 star times F2, different functions. Orthogonality tells us that the value of that integral will be 0. So all the integrals which contain F1 star will be 0. The only non-zero integral is this integral. Now we come to second term and multiply. This time that, different functions, F1 times F2 star, integration, because of orthogonality, that integral will be 0. F2 star times F2, that is normalization integral, result is 1. So the net result is, because this is 1, plus C2 square times K2 plus C3 square times K3. This is the final result from this calculation. Okay? So, what is this expression? You understand it from the left side. What does it say? Average value or expectation value. Average value of A, and then what are these numbers K1, K2, K3? They are eigenvalues of the operator A. Eigenvalues. All right. Now remember, what was the quantum mechanical postulate? When you make an experiment to find out, to measure a value of the observable A, the only possibilities are eigenvalues of the corresponding operator. All right? Here are those operators, eigenvalues, K1, K2, K3, but each eigenvalue is multiplied with something. These are weights of each eigenvalue, weight. So this is a weighted average. Weight factor for each eigenvalue is the square of the coefficient. Remember, sum of the squares of the coefficients is equal to we had done it before. Sum of the squares of the coefficients is equal to 1, because psi is normalized. So sum of the weight factors here, sum of the weight factors is 1. Therefore, we can interpret this expression on the right as follows. C1 square is the probability of observing eigenvalue K1. C2 square is the probability of observing eigenvalue K2, and so on. So each weight factor is interpreted as the probability of observing that eigenvalue. These ideas fit into probability theory because the sum of the weights is equal to 1. Here is an example. We are given the following property, set of functions. Assume the particle is in a state with a psi function given by a coefficient times f0 minus 2 times f1 plus 3 times f minus 2, where c is a constant. The functions are assumed to be normalized. Well, before stating the question, let me explain. The M, which takes these values according to the given information. M is an index which is attached to the function. So f minus 2 is some function in which m is equal to minus 2. f1 is another function in which m is plus 1. And f0 is a third function for which m is equal to 0. f0 satisfies this equation with m equals 0. f1 satisfies the same equation with m equals plus 1, which means the eigenvalue is 1 times h bar. And f minus 2 satisfies the same equation with m equals minus 2. So the eigenvalue will be minus 2 times h bar. Now, our general expression was this. But the numbering here is not the same as that one. This is the general notation. But what is important is that the right side is an expansion, isn't it? Because the left side is the state function, the right side contains several terms. So this is an expansion. This is a linear combination of eigenfunctions, f0, f1, f minus 2. So if you compare with that expression, here, how many coefficients are different from 0? Coefficient of f0, that is different from 0. What is the coefficient? C, right? What is the coefficient of f1 if you compare it with that one? It is minus 2 times C. What is the coefficient of f minus 2? It is plus 3 times C. That is a general expression, which means in principle there may be infinitely many terms. But when you see here, you don't see any other terms. What does it tell you? It tells you that all the other coefficients are 0. Only 3 coefficients are different from 0. Now we we can state the question. In measurements of property A, of the particle in this state, what are the possible outcomes for A? Possible outcomes for A. Now, what was the general principle? In a measurement of property A, only the eigenvalues of one of the eigenvalues of A can be obtained. And when we look at this expression, this is the weighted average of the eigenvalues. Only those eigenvalues with non-zero weight factors can be observed. So, what is the eigenvalue of this function? 0 times h bar 0. These are the eigenvalue of this function, f1, 1 times h bar, isn't it? Eigenvalue is here, 1 times h bar. What is the eigenvalue of this function? Minus 2 times h bar. Okay? Only these three functions have non-zero coefficient, which means if you compare it with this, only 3 terms are non-zero here. All the other coefficients are 0, therefore weights are 0. So if the particle is in this state, only one of these eigenvalues will be measurable. No other eigenvalue can be measured. So possible outcomes means which eigenvalues? And we are saying that only those eigenvalues whose weight factors or probabilities are different from 0. Okay. Then, the next part is, what is the probability of the outcome, of each outcome? Again, look at here. Probability of outcome K1 is what? It is the weight factor. Probability for outcome K2 is C2 square, and so on. Here, probability for this outcome is coefficient of F0. What is, using the symbol C, what is it? C. So this is the probability of observing this eigenvalue. Probability of observing h bar is the square of corresponding coefficient. What is the coefficient of f1? Minus 2 times c. Take the square, 4 times c square. Probability for this eigenvalue is equal to square of the coefficient of f minus 2. What is it? 3 times c. Take the square, 9c square. All right? Now, let us determine the value of c. For probability concepts to work, all functions must be normalized. Especially the state function must be normalized. this C, you see, is multiplying all terms inside the parentheses. Such a C is clearly called normalization constant. We assume C to be a real number. Then actually we had done this integral before for the linear expansion case. What was it? Sum of the coefficients, isn't it? So let us take the sum of the coefficients. C squared plus 4c squared plus 9c squared. One plus 4 plus 9. And this must be equal to 1. Therefore, square of C is 9, 10, 14, 1 over 14. And the actual numbers are 1 over 14, 4 over 14, and 9 over 14. These are the probabilities. And of course, the sum of the probabilities must be equal to 1. Okay, so this is how this idea about expansion of an state function into linear combination of eigenfunctions of another operator is done, and how the interpretation, especially the probabilities are simply the weights of the coefficients, which are squares of the coefficients. All right. Now slowly we are approaching the application part. We have, before actually starting with an important example, we need to talk about energy. Energy. And I'm going to use classical theory, classical mechanics, to point out some properties of total energy. But same remarks are valid in quantum theory also. Total energy. E. E is kinetic plus total energy is the sum of kinetic energy plus potential energy. Kinetic energy, let us consider just one particle and moving in one dimension. Let us say x direction. Kinetic energy is this expression. Range of p square means if you imagine all possible linear momentum values for the particle, what is the smallest value and what is the maximum value, highest value, and which numbers are also available between the minimum and the maximum value. Now, if this chalk is sitting there, what would you say about its momentum? You would say 0, isn't it? Therefore, the smallest value is 0. This is a positive number, p square. So all numbers are positive numbers. 0 to, is there any upper limit? No upper limit. So every number between 0 and plus infinity is possible for p square. And also, the numbers are continuous, aren't they? No jump from one number to another one. Continuous. We are talking about classical energy. All right. So, we are asking whether there is any arbitrariness in the kinetic energy. All right? If something is unknown about kinetic energy. Now, can we measure magnitude of linear momentum? Well, we can measure the speed of the particle. Is there any arbitrariness in measurement of speed? No. Therefore, a definite number can be found, no arbitrariness. From the speed, multiply it with mass, you obtain magnitude of linear momentum. Take the square, you will obtain p square. So, no arbitrariness. If there is no arbitrariness in p, there is no arbitrariness in the kinetic energy. Now, we come to potential energy. All right? Potential energy and force are related. This is the force, and if the corresponding potential is V, remember, for simplicity, I am considering just one particle moving along one dimension, so that this particle has only one variable, which I call x. All right. Now, force. Mass times acceleration. Is there any arbitrariness in measurement of acceleration? No, we can measure. Multiply it with mass, that's force. Therefore, no arbitrariness in the measurement of force. However, it is not true for potential energy, because if you replace V with V plus a constant, all right? Because this is a derivative, and derivative of a constant is 0, all of these choices for potential energy will produce the same force. Therefore, what do we conclude? There is an arbitrariness in the numerical value of the potential energy. All right? Numerical value of this C cannot be experimentally determined. Now, because of the arbitrariness in potential energy, there is an arbitrariness in the total energy, because that C also appears here because of the potential energy part. So the important point is that there is no such thing as absolute value of total energy. We cannot measure it is very different from absolute temperature, for example. There is a concept, absolute temperature, Kelvin, but no absolute energy, because numerical value of this C cannot be measured. Experimentally, only energy differences are measurable. Initial energy and final energy, the difference between the final and initial energies are measurable. In that case, this C will cancel. So keep this in mind, and we stop.